Hi, and welcome to our new session here in our Bayesian optimization chapter on noisy Bayesian optimization. So I've foreshadowed this a little bit already in the sessions before. So at least in most of the parts before, I assume that we are facing noise-free evaluations of cost function lambda. This is, I don't know, somewhat unrealistic. And practice, we usually observe a noisy readout. So usually if we, write this down mathematically, we could say, well, we're evaluating here our true underlying cost function, but there's some random noise on top of that, where at the end we observe this randomized version of C of lambda, which I'm calling y here. So y is cost plus this random noise epsilon. And of course, there are obvious sources of randomness in HPO. So there's random data, you're doing resampling, even if you would fix your validation set, it's still random, right? And also your learning algorithm might be, stochastic, maybe it's a random forest, it's a neural network using SGD as an optimizer, so you're not going to see the same result if you run this twice. And yeah, such noisy experiments are also very common, general computer experiments where you are also going to use Bayesian optimization if they're expensive to optimize them. So something that's quite important if you read papers on this, so very often, at some point you have to write down what you want to do inference on in the maths, and you can sometimes get a little bit confused whether you want to do inference on the y or inference on the c. So usually we're interested in this guy here, right? Because that's the true underlying signal. We're not interested in doing inference on this y. This y is what we observe. We're actually a little bit, annoyed by the fact that we don't observe this thing here. We want to do inference on this. So the first thing we can do is we can go from an interpolating model, from an interpolating Gaussian process, to a noise-aware surrogate where the Gaussian process acts as a regression model. So I have put that on the slides before. Maybe I haven't discussed this in depth because, but I mainly wanted to talk about the interpolating scenario in the slides before. So let's take a look at it here. So we actually do we have to change a very simple thing. So this here is the usual formula for the posterior mean and the posterior variance of our GP. And you can see here on the inside our kernel matrix K. You can see this both in the posterior mean and the posterior variance. And the only thing we have to do to go from an interpolating model to a well-formed regression model that respects this noise here and takes this into account is to add sigma squared epsilon to the diagonal of our kernel matrix before we quote-unquote invert it. And this reflects the noise in the evaluations of y, and this doesn't change the formula too much, right? And the nice thing about this is that we do not have to, prescribe this sigma squared epsilon guy here. We can learn that, again, by the same maximum likelihood principle that we use to learn the length scale parameters of the Gaussian process. So this is simply a part of the marginal log likelihood. We just optimize this, learn this in the usual manner as I have shown before. And when you do that, you now get a nice regression model that smooths through the data instead of interpolating it. Do we have to do something with the acquisition function? Unfortunately, the answer is yes. So potentially we have to change that as well. So I guess the first thing that comes to mind is that in the acquisition function here we have this C cost min guy, right? So the cost min guy is simply the minimum value of all of the costs we have seen in our archive. And in this case, this is now, we have observed these y variables. So we have observed these noisy y guys, right? So if we now take the minimum, that can be dominated by a lucky outlier, so to speak, a point which is only good due to random chance. So for PI and EI to work well, we would rather have a, well-formed C-min value, which really reflects the underlying true signal and not this observed noisy version of it. And this we usually do by creating something that's called a plug-in value for C-min. So we would replace this unknown Cmin, or instead of, I don't know, computing this thing here on the noisy values, we compute an effective best Cmin star by employing our surrogate model. So we actually compute the posterior mean, and then we potentially even do plus beta times the posterior standard deviation. So first of all, this already smoothes out the noise. This gives us a smooth version of the cost value, hopefully smoothing out the noise. And we might be even willing to add in a penalty. I was thinking, what is the opposite of reward? I guess it's penalty. A term for being very uncertain here. Yeah. So this second thing would make the, I don't know, computation, or would make the effective best computation even more risk averse, because we are downweighting uncertain points. Now there's already a very old, I guess old means here 20 years, noisy version of the expected improvement. That's by Wang et al. From 2006. It's called the augmented expected improvement. And that uses exactly the expected improvement now with this changed effective best C star min. But it also uses a correction factor here, which is based on the posterior uncertainty, but also here this estimation of this variance term sigma squared epsilon, which is sometimes also called the nugget effect in Gaussian process regression. And this penalty shrinks the acquisition function where the Gaussian process is already certain, and it redirects budget to replication and exploration. If this thing here goes to 0, you are pretty much going to standard EI, but this is a correction factor you are multiplying now on top of this changed EI with the smooth version of the Cmin. There's a newer noisy EI version. This uses the Monte Carlo generalization of reinterpolation. So reinterpolation is a method I haven't covered here on the slides, but maybe my comment makes sense if we look at how this works. So what we would do is we would draw plausible noiseless values at the design points from our GP posterior. So just draw a surface from the GP at the design points, and then we would refit now an interpolating GP to this. So we, at the design points, these are the training points of our GP, we sample from our current GP model, but we sample in a noiseless manner. And then we refit an interpolating GP, where we now pretend that this doesn't have any noise anymore. We compute a noiseless version of the expected improvement. This kind of gives us a complete function, an EI function across the whole design space. And then we do this multiple times, and we average all of these functions to get this noisy EI average version. And then we would optimize that. Of course, you can see this is somewhat more expensive because you have to do, multiple samples from your GP, you have to do multiple refits, but this gives quite good results in practice. Maybe I should also comment a little bit here on LCB. If you want to do something extremely simple, you could just use LCB without any changes, because there is no Cmin in the formula. So just using a nugget at GP alone suffices. Honestly, often this also works quite well. So if you want to have an extremely simple solution, use that. And there's the remaining aspect of which point do we actually return at the end when Bayesian optimization has terminated. So in general, there's a nice benchmark paper here by Pichini. It's now 10 years old on noisy Bayesian optimization. So maybe you want to also take a look into that. So one thing you could do is you could simply still return from your archive empirically the point with empirically the lowest cost value. But these were noisy, right? So vulnerable to lucky outliers, we already discussed that. So something simple you can do is you can simply smooth out again the noise in your archive by predicting on your archive with your surrogate model, and or you can do this risk-averse thing here, which we also discussed before here for exactly the same reasons. So if you're a little bit more uncertain about some points in your archive, you would put a penalty on these points. You can also do a replication or multiple replications, so you re-evaluate your incumbent to Shortman's estimate. On the other hand, if this now becomes worse than other design points, you might begin to think about how should I replicate these as well, how much budget at the end do I want to do, and then in a certain sense you're now talking about baking in a replication strategy into your BO algorithm, and I guess you would then rather have that in a principled manner, because it's unclear how often you're going to do this, especially if, I don't know, in a certain sense you fail or the results do not look like as you want them to be. You could also do a domain-wide evaluation of your posterior mean function across the whole configuration space and then return the best there. So this is effectively one extra iteration of Bayesian optimization with posterior mean as an acquisition function. Usually people don't like that because then you would return a point that you haven't even evaluated. I usually also would not do that. Okay, I wanted to say that this concludes our session here on noisy BO. Well, it nearly does. There's a nearly empty summary slide. Okay, so we have discussed how to switch to a nugget Gaussian process by also estimating the so-called nugget effect, sigma squared epsilon. We've talked about noisy versions of acquisition functions, augmented expected improvements, the plugin values there, noisy expected improvement, and that as a potentially simple choice just to use LCB without any changes. And we also talked about which point at the end we would return from our archive. Okay, and that concludes this session here.